All right, it's 8. Let's get going. We got stuff to do. So today we're going to start off by looking at some further complex power relationships. These are simply derived using our generic equation for complex power, which is S is equal to the RMS phasor voltage times the complex conjugate of the RMS phasor current. And then we're also going to use good old Ohm's law, which in the RMS phasor domain becomes V is equal to I times Z. And so from these relationships, we can actually derive expressions that will allow us to calculate the complex power over any impedance. Doesn't matter if it's a resistor, capacitor, inductor, or combination, knowing only the voltage phasor or only the current phasor. And we'll wind up using these relationships here in just a couple of minutes. So in terms of voltage, we could say that S is equal to V times I conjugate. So V is going to stay the same. Using Ohm's law, we can say that I is simply V over Z. So I'm going to have V divided by Z, and then the conjugate of this thing. So that's going to give me V conjugate times V divided by Z conjugate. Recall from our lecture on complex numbers that whenever I multiply a number by its complex conjugate, I simply get the magnitude of that complex number squared. So this in turn looks simply like the magnitude of our phasor voltage V divided by the conjugate of our impedance, or expressed slightly differently, just our effective voltage, no phase angle or anything like that, squared, divided by Z conjugate. In terms of current, we would have the following relationship. So S is going to be V times I conjugate. Using Ohm's law, I can be expressed as, V can be expressed as I times Z. Sorry, brain isn't working this morning. Times I conjugate. So this is going to look like I conjugate times I times Z, or the magnitude of our RMS current squared times Z, or I effective squared times Z. So these are our alternative relationships. Using these relationships, we can then make some simplifications for purely resistive, purely inductive, and purely capacitive loads. So for a purely resistive load, where R is greater than 0 and X is equal to 0, the complex power absorbed by a resistor can be expressed as simply the effective value of the voltage squared divided by the resistance value, or the effective value of the current squared times the resistance value. And we've circled all the way back around to our just basic DC power relationships here. So using effective values allows us to just use our DC relationships. For an inductive load, where R is equal to 0 and X is positive, we are going to have, in terms of voltage, J times our effective voltage squared divided by omega L. And in terms of our current, this is just going to be J omega L times I effective squared. One thing that I do want to point out here, if we look at our relationship here, I'm supposed to be dividing by the complex conjugate of the impedance. So we know that for an inductor, the complex conjugate of the impedance would be negative J omega L. But because that negative J is in the denominator, it's going to look like positive J in the numerator. So that's where that sign went. So I just wanted to be clear on that. Finally, for capacitors, or for a purely capacitive load, where R is equal to 0 and X is less than 0, or negative, we'll have SC is equal to negative J omega C times the effective value of our voltage squared, or negative J times the effective value of our current squared divided by omega C. I'm going to rewrite that J so it's not as sloppy. So looking at these relationships, what can we say about the complex power that's drawn by purely resistive, purely inductive, and purely capacitive loads? Well, let's look at the resistor first. Do you see any J's anywhere in this thing? No. So that means that the complex power absorbed by a resistor is only real. So it is the exact same thing as the average power, right? So resistors absorb average power. Okay. Looking at our relationship for a purely inductive load, we can see that there's no real term, right? So expressed as a rectangular complex number, we would have 0 plus J times this thing. We're always going to get a positive result because the square of the voltage or the square of the current is always going to be a positive number. So from this, we can say that inductors absorb reactive power. And for capacitors, we have the exact opposite situation. We are always going to have a negative result because there's always going to be a negative sign out front, and all of our other quantities are going to look like positive numbers. So we can say that capacitors supply reactive power. We're going to use these relationships again here in just a few minutes when we talk about the concept of power factor correction. So before we move on to power factor correction, does anybody have any questions, comments, or concerns about any of these relationships? Yes, sir. Right. So if we were to look at a complex plane here, right? So here are our real numbers and here are our imaginary numbers. If I have a generic impedance Z, the real part of Z is the resistance, and the imaginary part of Z is the reactance. So for a pure resistive load, that would be something that lies on that horizontal axis, right? So R is greater than 0 and X is equal to 0. We know that we have no phase angle, so there is no imaginary part whatsoever. For a purely inductive load, our reactance is positive, which means we're going to vertical axis, but we're going to be on the top half of the plane, right? So we have no resistance, we have positive reactance. For a capacitive load, or a purely capacitive load, X is going to be a negative number. So we'll be somewhere like down here. Is that adequate? Okay. Any other questions about these relationships? One thing that I want to point out just really quickly while I have this graph up, I'm not sure that I've mentioned it to this point. We know that the angle theta z is equal to theta v minus theta I. This is the exact same definition as our power factor angle, theta s. So if we ever wanted to know what power factor an impedance was operating at, if we know the phase angle of the impedance, we have enough information to determine the power factor at which that impedance is operating without doing literally anything else. We don't need to do any circuit analysis whatsoever, since theta z and theta s are literally the exact same thing. So we can use that to our advantage if we so choose. All right. So I want to start our discussion on power factor correction by working an example. So let's say that I have the following circuit where I have some source voltage, Vs, operating at a linear frequency of 60 hertz. So this system is somewhere in America or North America. And I am going to connect this source via transmission lines, which our transmission lines are going to be characterized by some resistance and some reactance. So let's call this 0.1 ohms and then J 0.2 ohms. So let me just put a little note here. And I'm going to use this source to provide power to several loads. So instead of describing the load using an equivalent circuit model, I'm actually going to describe the load here based on the power that it's drawing. So this is a way that you could approach problems, particularly from an industrial standpoint, where you don't really care what the load looks like. You only care what it draws and what power factor it's operating at. So let's call this guy load number 1. And let's say that it draws 30 kilowatts at a power factor of 0.8 lagging. And let's put a second load over here. And let's say that it draws 25 kVA at a power factor of 0.9 lagging. And let's put a third load over here. let's say that it draws 10 kilowatts at a power factor of 0.88 leading. Let me draw that a little bit better so that we can see. 0.88 lead. There we go. We can measure the voltage drop across our 3 loads in parallel, and we find that the voltage here is 480 angle 0 degrees volts RMS, and I want us to find the power factor at which the source supplies power and the value of Vs. So, unless I'm vastly mistaken, this is the first time you guys have ever seen a circuit expressed in this form. And so we are going to have to think about what our steps should be in order to solve something like this. Okay? So I would argue that in order for us to find the power factor at which our source is supplying power, we need to determine the complex power supplied by our source. That seems like a reasonable place to start, because if we have our complex power supplied by our source, we have effectively all of the information about our source, including power factor, right? So going way back to the second day of class, we talked about a little something called Teligens's theorem. Teligens's theorem effectively stated that the power supplied in a circuit has to equal the power absorbed in a circuit. So realistically, we could say that the power supplied by this source, which based on our current level of information would be difficult to get in one step, is going to be equal to the total amount of power absorbed in our circuit. So we would need the complex power absorbed by load 1, complex power absorbed by load 2, complex power absorbed by load 3, complex power absorbed by our transmission line network, add all those together, and whatever that makes is what the source has to be supplying. Seems like a reasonable argument. And that is the exact approach that we're going to take. So I'm going to start by figuring out what the complex power absorbed by each of my loads are. And it may not seem like we have enough information here, but I guarantee you that we actually do. Okay. So let's start by looking at the complex power absorbed by load 1, which I'm going to call SL1. Okay. So we were given the power factor, which is 0.8 lagging, and we were also given 30 kilowatts. So does that 30 kilowatts represent apparent power, average power, or reactive power? Average power, because the units are in watts, right? So recall from our definition of power factor, I'm going to put it here in blue, that power factor is defined as the ratio of the average power to the apparent power, which is the same as the cosine of the power factor angle. I can rearrange this expression, and what I'll find is that the complex power absorbed by load 1 is going to be the average power absorbed by load 1 divided by the power factor of load 1 with a phase angle of the inverse cosine of the power factor of load 1. Meaning that if I know power factor and average power, that's all the information I need in order to determine the complex power absorbed by that load. Okay. So if I put my numbers in here, this is going to look like 30 kilowatts divided by 0.8 with an angle of inverse cosine of 0.8. I'm going to talk this into my calculator here. I get 37.5 with an angle of 36.870 degrees kilovolt amperes in polar form. And just for the heck of it, in case we need it in a little bit, 30 plus J 22.5 kVA in rectangular form. So before we move on to load 2, anybody have any questions about this calculation? No black magic or wizardry or anything like that. It is just algebra for relationships that we've already developed. Okay. So let's look at load 2 now. So once again, we're given the power factor. We're also told that we are operating or drawing 25 kilovolt amperes. Is this apparent power, average power, or reactive power? Apparent power. So apparent power is the magnitude of the complex power. So in this particular case, we're not going to have to divide P by the magnitude of S because we were already given the magnitude of S, right? So we're going to have the magnitude of SL2 with an angle of the inverse cosine of the power factor of load 2, which in this case is going to look like 25 kVA with a phase angle of the inverse cosine of 0.9. Let me throw that in my calculator. We'll talk about that in just a moment, which is why I have one of these leading so we can see what it affects. Good intuition there. So we wind up getting 25 angle 25.842. And expressed in rectangular form, this looks like 22.5 plus J 10.897. Any questions about that particular calculation? All right. So for load 3, we're going to have the average power because we were told the power in kilowatts. So this is going to be PL3 divided by PF for load 3 with an angle of inverse cosine of PFL3. Now, to answer Christina's question, how do we take into account leading and lagging? Well, so what do we know about a lagging power factor, the angle for a lagging power factor specifically? Positive, right? The inverse cosine function is always going to give us positive angle. For load 3, we were explicitly told that our power factor is leading. So in order for us to get a negative angle out of this inverse cosine operation, we simply have to put a negative sign out front, and that'll take care of the fact that our power factor was lagging. Or excuse me, leading. My apologies there. Okay. So this is going to look like 10 kilowatts divided by 0.88 with an angle of negative inverse cosine of 0.88. Excuse me. And I get 11.364. With an angle of negative 28.358 degrees kilovolt amperes, and expressed in rectangular form, this looks like 10 minus J 5.397. I'm going to add all of these together. And find the total power absorbed by what's called my composite load. So that's just going to be SL1 plus SL2 plus SL3. And I get 68.485 with an angle of 24.132 degrees kilovolt amperes in polar form, or 62.5 plus J 28 kVA in rectangular form. All right, so we're about 2/3 of the way finished with this thing. So we figured the total complex power absorbed by our three loads. Now we need to figure out the complex power absorbed by our transmission line network. Any thoughts on how we might do that? So I would argue that based on the relationships we learned about right before we started working this example problem, we need either this current, which I'm going to call I wire, or this voltage, which I'm going to call V wire. Either one of those will get us the answer that we're looking for, right? We can, if we just know the current, we can do the magnitude of I squared times the impedance of the transmission line gives us our complex power. If we know the voltage, it's the magnitude of the voltage squared divided by the complex conjugate of the impedance of the transmission line gives us our complex power. So which of those two quantities can we actually solve for based on what we know currently? Well, I would argue it needs to be the current, because in order for us to find that voltage, we would have to do Kirchhoff's voltage law around this system. And we don't know what Vs is. So that's too many unknowns for us to handle. So I would argue that the current flowing through our transmission line has to be the current flowing through each of these loads added together. Now, I am not going to find those individual currents because I don't need to. Since I know the total complex power absorbed by those loads, and I know the voltage drop across those loads, that's enough information for me to find the current. So effectively, what I am saying is that S total is that 480 angle 0 degrees volts RMS times the complex conjugate of my current I wire. Right? So just to be clear here, just using our relationship, current IW is flowing into the positive polarity terminal, so that's where my signs work out that way, all that kind of good stuff. Right? I can rearrange this and find that I wire conjugate is going to be S total divided by that 480 angle 0 degrees volts RMS. And in order to get rid of the conjugate on my current, I'm going to effectively do the conjugate of both sides. So if I double conjugate something, I'm just changing the sign on the imaginary part twice, which is the exact same thing as getting rid of that conjugate operation on the current. To be very clear, the conjugate of a fraction means that I conjugate both the numerator and the denominator. So this is going to look like 64.485 angle negative 24.132 degrees kVA divided by 480 angle negative 0 degrees volts RMS, where I know that there is no difference between positive 0 and negative 0. I'm just trying to make sure that you guys all understand we need to conjugate both the numerator and the denominator here. Putting this in my calculator, I'm going to have conjugate of P divided by 480. So that's giving me 0.1426 blah, 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 but that's because we're dividing kilovolt amperes by volts RMS, so that's giving me a current in kiloamps. I probably want my current to just be in amps, so let's call that 142.678 with an angle of negative 24.132 degrees. Amps RMS. From here, complex power absorbed by my transmission line network is just going to be the magnitude of IW squared times ZW. So that's going to look like 142.678 amps RMS quantity squared. And my impedance from above was 0.1 plus J, sorry, I scrolled too far, 0.2. Magnitude of A squared times 0.1 plus 0.2 I get 4,551.951 with an angle of 63.435 degrees. volt amperes, or 4.552 with an angle of 63.435 degrees kilovolt amperes. The total complex power supplied by my voltage source must equal the complex power absorbed by my composite load plus the complex power absorbed by my transmission line network. And so adding those results together, I get 72.065 with an angle of 26.425 degrees. Or in rectangular form, 64.536 plus J 32.07 degrees. Sorry, both of these are expressed in kilovolt amperes. All right. So we've done all of this work. Now we can actually start answering the questions that we were asked. So if I want to calculate the power factor at which my voltage source is supplying power, what do I need to do? Shouldn't be a trick question. We did this exact thing yesterday or Monday or whatever. Cosine of the angle. That's it. So the power factor at which our voltage source is supplying power is the cosine of 26.425 degrees. So cosine of angle of, we have to save the C, 0.896. Is this leading or lagging? Lagging, why? Exactly right. So there's the answer to the first question. I'm going to put a box around this because we're going to use it here in a moment for something else once we talk about power factor correction. How am I going to find my voltage? So I would argue that SVS, remember that this is supplied complex power here. We're trying to find the complex power supplied by our source, is going to be the voltage drop across our source times the conjugate of the current entering the negative polarity terminal of our source, which is just I wire, which we already found. So VS is just SVS divided by IW conjugate. So having to look back to see what I saved these things as, I believe this is going to be C divided by conjugate of A. I get 505.092 angle 2.293 degrees volts RMS. I'm also going to put a box around this. We're going to use it momentarily as well. All right. So we've worked this example problem. Now, actually, does anybody have any questions about this before we talk about power factor correction proper? Exactly right. Yep. Okay, so from this example, we can see that our source for this system is operating at a power factor of 0.896 lagging. While this isn't particularly low, it is lower than the threshold that most electric utilities would prefer that we operate at, okay? So an electric utility prefers that we operate usually at somewhere between 95 to 97.5% power factor, and this 89.6% is less than that, which means that as it stands with this particular load, the user would be fined some amount of money because we're effectively wasting the electric utility's resources. So what we're going to talk about now is the different options that we have in order to correct power factor or make it appear as if the power factor is at an acceptable level, and how to accomplish that. So let's look at a graph. So this is going to be simply the power triangle for an inductive load. Here is our real axis. Here is our imaginary axis. And let's do it in purple. This is our complex power, either absorbed by our load or supplied by our source, whichever way we care to look at things, right? Once again, the projection of this complex power onto the real axis gives us our average power, and the projection onto the imaginary axis gives us our reactive power. I'm going to use the subscript old here to denote that this is what the system looks like prior to power factor correction. Okay. And while I'm at it, let's go ahead and identify this angle, theta old, as well. So if we want to increase the power factor at which this system operates, do we need to make our angle theta larger or smaller? Smaller, because the cosine of 0 is 1, and that's our best case scenario, meaning that we're operating at 100% efficiency. So we want our angle to be as close to 0 degrees as possible. So there are two ways that we can accomplish this. One is generally wildly stupid, and the other one is how it's actually done. So let's talk about the wildly stupid way first. Okay. So what I'm going to do is I am going to draw the complex power line or vector here for a case where we are holding Q old to be constant, but we are increasing the amount of average power absorbed by our system. So something like this. We could call this S nu. The reactive power, once again, has stayed completely constant. P nu has increased, and therefore theta nu is smaller than it was before. So if we could figure out a way to make our load absorb more average power, that would increase our power factor. Everything tells us that it'll work. The problem with this, or the reason why it is wildly stupid, is average power is what the consumer pays for. So effectively, this represents running up your utility bill in order to avoid paying a fine. In practice, it makes no sense whatsoever, but mathematically, it absolutely does what we want it to do. Yes, that is exactly what that is. So now let's take a look at what an actual established manufacturing center or something like that would do. Okay. So instead of doing this thing, let's erase this pink line here. This is the arguable bad way to do it. What if instead we were to lower Q while holding P to be constant? Right? So something like this. Our angle is smaller, which means our power factor has been corrected. Our average power has remained constant, which means we're not incurring any repetitive costs by doing this because we're not running up our bill month by month by month. So whatever we do to decrease our Q is really just a one-time cost, hopefully, right? So this is the way that power factor is traditionally corrected in an industrial system. Now, let's talk about how this is done practically. We are effectively being required to inject some amount of negative absorbed reactive power into our system, right? So this guy right here, vector pointing down, is what we're adding into the system in order to make this happen. What element do we know that's going to give us a negative absorbed reactive power with no real component whatsoever? A capacitor, absolutely right. So I'm going to call this down here S cap. So we're going to put a capacitor into our system in order to correct our power factor. Let's do some math here really quickly. So earlier on, we said that S cap was equal to negative J omega C times the magnitude of the effective voltage squared. S old is simply P old plus JQ old. And S new is P old plus JQ new. The complex power that is provided by our capacitance is simply going to be S new minus S old which comes out to be J Q new minus Q old. This quantity will always be a negative number. And we can call this J times Q cap. So if we equate our two relationships for S capacitor, we can actually solve for C that will let us know what value of capacitor we need to put in to our system based on our understanding of what really theta old and theta new are. We'll talk about that in a moment. So we can find that C is going to be equal to negative Q cap divided by omega times V effective squared. So this is one form, and it's a perfectly acceptable form, but it's not the one that I prefer. Another way to express this, and the negative sign is not here, I want to be clear about that, is as follows. So P old times the tangent of theta old minus the tangent of theta new divided by omega times V effective squared. And the reason why I prefer this relationship is because typically figuring out what theta old and theta new are is a little easier than figuring out what Q cap is. So let's revisit our previous example problem. So I'm going to be lazy and just steal this diagram. I want us to recall that we found the complex power of our source, bless you, to be 72.065 with an angle of 26.425 degrees kilovolt amperes. And we also found our source voltage to be 505.092 with an angle of 2. Let's scroll up here so I have to do this. 293 degrees. Volts RMS. So what I want us to find is the capacitance needed to increase our power factor of the voltage source to 0.95 lagging. All right, so one other thing really quickly that I'm going to do here is I'm just going to illustrate where our capacitor is placed in this system. So since we are correcting the power factor at which our voltage source operates, we just want to place our capacitor directly in parallel with our voltage source, right? So this is going to take into account the lagging contributions of all of our composite load, as well as the lagging contribution of our transmission line. It is possible to correct the power factor of loads individually, but it is more economically feasible to perform your power factor correction effectively at your transformer and transform everything downstream instead of doing multiple iterations of power factor correction for every load that's connected, which is why I'm showing you this particular configuration. So let's talk about what information we already have, okay? So do we have P old? So P old is the average power supplied by our voltage source in this system. So P old is simply going to be the real part of SVS, which I gave it to you in rectangular form earlier. The real part of what I have stored in my calculator is C, 64.536 kilowatts. Do we have theta old? Exactly right. 26.425 degrees. Do we have theta nu? Yep, absolutely. Inverse cosine of 0.95. (18.195 degrees). Do we have omega? Exactly right. So 2 pi times 60 hertz is 120 pi radians per second. Do we have the effective value of the voltage drop across our capacitor? The voltage drop across the capacitor is just Vs. So we just need the magnitude, 505.092 volts. Now that we have all of those pieces of information, or have identified that we actually already knew practically all of them, we simply plug those numbers into our calculator, into our equation, call it a day. So let's see here, 64,536. So I'm dealing with watts so that my units will come out okay, times the tangent of 26.425 minus the tangent of 18.195 divided by 120 pi times 505.092 squared. I get C to be equal to 112.906 microfarads. Nope. Micro, that is correct. 10 to the negative 6 microfarads. Yeah. So we just put omega in directly, no need to change the angle or anything like that. The only time we're ever going to have to do that conversion is when we're calculating the value of a time varying sinusoidal function, which this is not one of those cases. Okay. So just as a quick aside here, 0.95 lagging is a pretty standard value. Let's look at 0.95 leading, right? So if we wanted C needed to increase our PF to 0.95 leading, what's the only piece of information that we would need to change for this calculation? Theta nu. Everything else is exactly the same. So negative, the inverse cosine of 0.95, that should literally just change the sign of the angle. Yep. So negative 18.195 degrees. Plugging in our values for this, let me do this again. 64,536 times tangent of 26.425 minus the tangent of negative 18.195 divided by 120 pi times 505.092 squared. 554.010 microfarads. Significantly larger capacitor value, roughly 5 times as large, which generally would be 5 times more expensive. So from the electric utility standpoint, it really doesn't care if your power factor is 0.95 lagging or 0.95 leading. It just wants it to be as close to 1 as possible. The most economic way to do this is to operate at a lagging power factor because it's going to require a smaller capacitor to get there. All right, so that is enough out of me for today. Unless anybody has any questions, I believe you have an in-class assignment and a lab. I would probably work on the lab. I have the oscilloscope probes there on the table. You'll need 2 of those. I also have your function generator leads. You'll need 1 of those. And then I have 10 nanofarad capacitors in that envelope so that there's no worrying about having the right size capacitor. I've provided them for you. One last thing that I want to mention, thank you guys for toughing this out and all this kind of stuff, especially after the less than stellar exam 1 scores. There is going to be a survey that's going to go out today via email. It's effectively like an end of course survey asking about how you think about, or how you feel about your ability to perform different calculations and analyses, all that kind of good stuff that we've done throughout the duration of this class. And then at the end, I believe there are 4 open-ended questions about, what's your favorite part of the class? What's the part you like the least? What do you think about the labs? What can I do to improve, and all that kind of good stuff. I would appreciate it greatly if you took the time, maybe 5 minutes or so, to actually fill that survey out so that hopefully sometime in the next several quarters, I can make this class less terrifying. All right, thank you guys again, and do the lab.